All right, so the next thing that I want to go over, and we are leaving the original section beforehand, kind of leaving probabilities and all of that behind, and we're going to move on to the geometry section. Now you notice the geometry section is the longest section. There's a lot of stuff in there. Some of what I'm going to show you is a little bit different. Some of the stuff that I'm going to show than what they're going to talk about. Some of the stuff is going to be useful for later years. It'll help you in things like physics and things of that nature. So before we do that, we're going to talk about the very basic building block of a lot of what we do in mathematics in general, and that is the use of the triangle. And what we find out is that 90% of what we do with the triangle actually winds up coming back to one of our favorite old school things. Every single one of you should know it. The Pythagorean Theorem. If you don't know what it is, I'm trying to figure out how on earth you got through 8th grade math. You've been doing this for a very long period of time, the Pythagorean Theorem. Stated simply, the Pythagorean Theorem says, assuming that you're given a right triangle that is a right triangle with legs length A and length B, and a hypotenuse length C, the Pythagorean Theorem states that the square root of the A plus the square root of the B is equal to the square root of the C. There will be some questions that will be just straight up Pythagorean Theorem questions. The only rule is you have to have a right triangle, and if it's not a right triangle, you're good. But let me ask you this. Let's say I give you a weird and unique situation. What if it weren't a triangle per se, but rather, what if I gave you a rectangular box? And in this rectangular box, wow, that's a really bad box. Let me try it one more time. All right, rectangular box. I'm going to do it this way. Let's assume we have, do it this way. Do something like this. Something like that. There we go. I can deal with that. That's a little bit better. Let's say I've got this rectangular box. Get rid of that piece. That should also be. And let's say I wanted to know what's, given this box, I don't know, is 3 foot by 5 foot by 7 foot. And I want to know if what's the largest pole, I'm going to use a pole specifically, we can place in the box. And to simplify my definition of a pole, I'm going to ask what is the largest, it's going to be no extra dimensions, it'll just be essentially a line. And if we're looking at this particular problem, some people might say that the answer is 7 foot, and I'll guarantee you in a multiple choice there would be a 7-foot pole. But there's actually a length that's going to be a little bit longer. We could actually take this, and I realize my picture is terrible, but I could actually take a pole that goes from this corner all the way up to this corner, and if I put that pole in diagonally, that's actually going to be the longest distance. So how on earth does this work? We've got to figure out what that is. And what we find out is that Pythagorean Theorem could actually work in 3 dimensions as well. See, Pythagorean Theorem isn't unique to a 2-dimensional triangle. But in a 3-dimensional triangle, if we let this equal A, this equal B, this equals C, and this be some length D, what the Pythagorean Theorem in 3 dimensions says is that the D squared is going to equal, the D squared is going to equal the sum of the 3 sides perpendicular to each other. How A to B is perpendicular, B to C is A to B is perpendicular, B to C is perpendicular. And even if you look C to A is also perpendicular. So in this particular question, the largest pole we could fit, D, is going to equal to the square root of 3 squared plus 5 squared plus 7 squared, which is going to equal the square root of 9 plus 25 plus 49. And we go through and figure out what that is. I don't really want to figure out what that is by hand, so let me go ahead and do it this way. If I do 9 plus 25 plus 49, I take the square root of 83, we find out we can fit a 9.11 foot pole into that box. Now most people probably wouldn't think about that. That seems like a long, too long of a pole, but remember, if we throw it in at a diagonal, we're good. That's about all I want to do with the Pythagorean theorem. That's 6 minutes, but that was a three-dimensional problem, so that makes life interesting. What I really want to get into now are triangles. And maybe some of you have heard about these things called special right triangles. All right, and I'm just going to take a minute to talk about them. And special right triangles are these triangles that follow, there's two different ones that you need to know. There is the ever so lovely 45, 45, 90 degree triangle. So this is a 45, 45, 90. The next one is a little bit different. This turns out to be a 30, 60, 90. Now the 45, 45, 90 is probably the easiest because in a 45, 45, 90 my legs are going to be equal to each other. So let's real quick do the 45, 45, 90. In a 45, 45, 90 triangle, my legs are the same. If I call that length A, then this length would also be A. And since this is a right triangle, we can use Pythagorean theorem. We can say that A squared plus A squared is equal to C squared. And if we did that, we'd realize we'd have 2A squared is C squared, or C could be written as the square root of 2 times A. Now this seems kind of weird, but what the power of this is if I know that I have a 45-45 triangle, if I've got something where this is the case, and I've got some 45-45 triangle, and I tell you that this is equal to 6, and I ask you what is the length of the hypotenuse, there's a lot of things I could do, but and one of them being the Pythagorean theorem. But if I know it's a 45-45 triangle, I know that all I have to do is say, well, C is the square root of 2 times A. This is just root 2 times 6, or 6 root 2 if you wanted to simplify that. Now, I'm not a huge fan of this. I'm just showing you this so that we can have it. So then we come to the next triangle. I'm going to go back real quick in the 30-60-90 triangle. Now in a 30-60-90 triangle, that gets a little bit weird. For a 30-60-90 triangle to actually show you how this works, what I would have to do is I'd have to actually not draw a right triangle, but I would actually have to draw an equilateral triangle. All right? And if I had my equilateral triangle, let's call one of these sides just a side length A. What I can do is I can realize if this is a 30-degree angle, and if I draw a vertical line along here, all right, then theoretically if this is perfect and this is a 90-degree angle, then this should be half of that this should be half of that A. So this would become 1/2 A. And all we'd have to do is figure out what on earth is that last side. Utilizing Pythagorean theorem, we could say that A squared is equal to 1/2 A squared, 1/2 of A squared plus whatever this x squared is. So this gives me A squared minus or equals, I'll do it this way, 1/4 a squared plus x squared. Subtract the 1/4, I could get 3/4 a squared is equal to x squared. And if I take the square root of both sides, I get the square root of 3 over 2a is equal to x. Now that looks kind of gross. So one of the things that we like to do is we don't like to have these in terms of fractions. So what I'm going to do is I'm going to take this triangle and I'm going to multiply each one of these sides by 2. So if I multiply this by 2, this just becomes a. If I multiply this by 2, oh, by the way, this should become a 60, and this is my 30. I apologize. This becomes a square root of, times 2 becomes a square root of 3a, and this becomes 2a. And in a 30, 60, 90 triangle, we have a 30 side, a 60 side, and a 90 side. The short side is always going to be called a. The next side is going to be called the square root of 3 times a. It's a little bit longer. Square root of 3 is bigger than 1, but the square root of 3 is also smaller than 2. And we can use that relationship. Now, having done all of this, this is not my favorite way of dealing with right triangles. I wanted to show you this because if they do a problem with special right triangles, they can come up like this. What I want to now do is show you another means of dealing with problems with special right triangles that I am a fan of. And it requires the 3 buttons that you've probably played with on a graphing calculator before, but you have never really used. I don't know why that's as small as it is. Is there a way I can make it bigger? I'll deal with it later. And the ones I'm specifically talking about is the sine. That's not sin, that's sine. The cosine and the tangent. And those are what are called the trigonometric functions. See, here's how this works. We're going to have a right triangle. And again, sine, cosine, and tangent, again, only work for triangles, for right triangles. And I'm going to look at this angle theta. Don't worry about the fact that it's a weird looking symbol. It's just another symbol like x, y, and z. All right? And what I'm going to do is I'm going to label these sides, but I'm going to label them kind of weird. I'm going to call this side right here the opposite side of my theta. It is the piece that's completely removed from my theta. And I'm going to call this leg right here my adjacent. Finally, I'm still going to call this the hypotenuse. And with this information, we actually can come up with these trig relationships. And what these trig relationships are is the sine of whatever that theta is, or the cosine of whatever that theta is, or the tangent of what that theta is. Those are all ratios of my triangle. The sine is the ratio of our opposite side over our hypotenuse. The cosine is the adjacent side over the hypotenuse, and the tangent turns out to be the opposite over the adjacent. What I mean by that is if I wanted to find, say, the cosine of a 60-degree angle, okay, then in this case it would be the opposite side over the, the adjacent side over the hypotenuse. Well, let's go back real quick. This becomes an interesting thing. So I said the cosine of 60 would be my adjacent over my hypotenuse. The adjacent is the one that's touching, the leg that is touching, so that would be A over the hypotenuse, which is 2A, and we find out that the cosine of 60 is 1 over 2. If I wanted to find the sine of 60, which is my opposite over the hypotenuse, what I would do is I would use the fact that the opposite of this is the root 3a, and the hypotenuse is 2a, and I would call this root 3 over 2. And what we wind up doing is we can use this to assist us. one of the questions they pose, and they do this really weird special right triangle thing. But what they say is that you've got a right triangle that's a 30, 60, 90 triangle. Okay? And then what they did is they said, and we're going to draw a new triangle right here that is also a right triangle. They tell you in the picture that this is a 30. And if this is a 90 and that's a 30, then this has to be a 60. Now what it means is that this right here is also a 30. So you got some similar right triangle things going on. And what they do is they use similar right triangles and the special relationships between to try to come up with what this particular point is here. And they say right here is 5. What I'm going to say is, what if we didn't want to do it that way? See, I can use Trig to help me. As I go through and I look at this particular thing, I know that this 60 right here, I could figure out what this missing side is. And this side, if I think about just what these sides would be, let me label this. Let's say I've got a triangle A, B, C, then I know that I also have a triangle that's similar to it that would be A, B, C. And because I have these right triangles, I can actually use Trig in order to find it. You see, if I can find this length B, then I can use the Trig to find B because I know what the opposite is and I'm just looking for the adjacent and I have an angle. If we look back at my relationships that I mentioned, the one that is an opposite over adjacent is a tangent. So I can say that the tangent of 60 degrees is equal to my opposite over adjacent, or in this problem, it's 5 over my big B or C, whichever one you want to call it. So what I can do is I can use some math here now, and I can call this B is equal to 5 divided by that tangent of 60. Now, if you're in my AP class, you should be able to come up with that answer with fair ease. If you're not, you would take your calculator and you would write 5 divided by, one thing, and we'll make sure that this is corrected no matter what. If that's what I wanted my mode. So I thought, before you go into the test, I will make sure that this is corrected. You do not need to know how to change between radians and degrees, so lucky you. But what I can do, get out of there, there you go. I can do 5 divided by the tangent of 60. And this is going to give me some really disgusting number. We're going to hold on to that. That big gross thing, that's a number. All right? Oops. So this is now 5 over whatever that tangent of 60 is, which is some like 2.88. Let's take it to, I don't want to really round it, 2.8867. Let's use 5 decimal points. That should keep us pretty safe there. All right, so now I've got this piece, and now I've got a 60-degree angle here. Well, so with that 60-degree angle, what I can say is I've got an opposite, and this is labeled C. This is now a hypotenuse. So I go back and I say, what's the opposite over the hypotenuse? That turns out to be a sine relationship. So now what I can do is I can say that the sine of 60 is equal to my B over that 2.8867, so that's 4 decimal points. And what I can do is I can use my calculator here. And I can take that 2.88675 blah 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 and multiply that by the sine of 60. 2.5. That's a pretty clean answer. And you get your answer. This is just an introduction. I will try to work a couple more special right triangle problems, SOHCAHTOA style things. What you may want to do is just look online and look up just basic trig things if you're not sure about that. My people who have taken geometry already will be at a definite advantage. My freshmen, I'm sorry, you're kind of a little lost in this case. Where I'm going to go next is the coordinate geometry section and start that up for you all as soon as I get a chance. So hopefully this was good for you. At least remind you maybe some ways to attack these problems. And I'll put up another video soon.